Hello friends, in last lecture we covered the basics of flip-flop, that is 1 bit memory cell. Now conclusion of 1 bit memory cell is Q and Q bar are always complements of each other. Then second conclusion, if Q equals to 1 and Q bar equals to 0, then this state is called as logic 1 state or set state. Similarly, if Q equals to 0 and Q bar equals to 1, then this state is called as logic 0 state or reset state. Now in this lecture we will cover the first type of flip-flop, that is SR flip-flop. Now what is SR flip-flop? Now for SR flip-flop there are total number of two inputs, that is S and R. Now S is also called as an set input and R is also called as an reset input. That's why this type of flip-flop is also called as an set reset flip-flop. Now SR flip-flop has two outputs, that is Q and Q bar. The Q output considered as a normal output and the other output, that is Q bar, is just a complement of Q. Now we can design SR flip-flop by using universal gates. It can be either by using NOR gates or NAND gates. Now let's design SR flip-flop by using NAND gates. Now if you see the circuitry, then total number of two NAND gates are used, that is NAND gate 1 and NAND gate 2. Now input to your NAND gate 1 is reset, that is R, and output of NAND gate 1 is Q. Similarly, input to NAND gate 2 is set, that is S, and output is Q bar. Now this circuit is also called as a cross-coupled NAND gate. Now why cross-coupled NAND gate? Because the output of first NAND gate is one input of second NAND gate. Similarly, output of second NAND gate is one input to the first NAND gate. That's why this circuit is also called as a cross-coupled NAND gate. Now second table indicates the truth table of SR flip-flop by using NAND gates. Now as total number of inputs are 2, that is S and R, so total number of 4 input conditions according to the equation, that is 2 raised to n, where n indicates total number of inputs. Now here total number of inputs are 2, so 2 raised to 2, that is equals to 4, so there will be 4 input conditions will be there. Now which are the 4 input conditions? Now first input condition, if suppose S equals to 0, R equals to 0. Then second input condition, if suppose S equals to 0, R equals to 1. Similarly, S equals to 1, R equals to 0. And last condition, if suppose S equals to 1 and R equals to 1. And second table indicates the outputs, that is Q and Q bar. As we know, Q is the normal output and Q bar is just a complement of Q. Now for first condition, if suppose S equals to 0 and R equals to 0, then our flip-flop will be in rest condition. Now what is rest condition? This I will explain in next slide. Similarly, what will be the outputs for 0, 1, that is Q equals to 0 and Q bar equals to 1. Similarly, when S equals to 1, R equals to 0, then why Q equals to 1 and Q bar equals to 0. Similarly, if suppose S equals to 1 and R equals to 1, then why Q equals to and Q bar equals to no change. Now this I will explain in next slide. Now for first condition, that is case 1, if suppose S equals to 0 and R equals to 0. Now let's move towards the circuit. Now in circuit, S equals to 0 and R equals to 0. Now as per the truth table of NAND gate, we know if any one input to the NAND gate is low, then output is high. Means for first three conditions, that is 0, 0, 0, 1 and 1, 0, output of NAND gate is always equals to 1 because one input to the NAND gate is low, that's why output is high. Similarly, if both the inputs are high, then and then only output will be low. That is the conclusion of the truth table of NAND gate. Now to check the first condition, that is when S equals to 0 and R equals to 0. Now when S equals to 0 and R equals to 0, both Q as well as Q bar are forced to be equals to 1. Because as per the truth table of your NAND gate, if any one input is low, then output is compulsory to be equals to 1 or high. Now as we know, the conclusion of 1 bit memory cell, Q and Q bar are always be complements of each other. Complements of each other means, yes, if suppose Q equals to 0, then Q bar should be equals to 1. Similarly, if suppose Q equals to 1, then Q bar should be equals to 0. But when S equals to 0 and R equals to 0, for this condition, Q and Q bar are compulsory to be equals to 1. So this state is also called as an indeterminate state, or hence we are going to avoid this state, and this condition is also called as an rest condition. Now second condition, if suppose s equals to 0 and r equals to 1. Now if suppose s equals to 0 and r equals to 1, then according to the truth table of NAND gate, if any one input to the NAND gate is low, then output is considered to be high. Now for second NAND gate, that is NAND gate 2, input is 0, that is s equals to 0. So output should be equals to 1. So when s equals to 0, then it forces, that is q bar, to be equals to 1. Now as q bar equals to 1 means one input to first NAND gate will be equals to 1 and already r equals to 1. So when both the inputs are equals to 1, then output of that particular NAND gate will be equals to 0. So the output of NAND gate 1, which is equals to 0, means q equals to 0. Now when q equals to 0, then q bar equals to 1. Thus, when s equals to 0 and r equals to 1, the outputs, that is q equals to 0 and q bar equals to 1. And as we know, when q equals to 0 and q bar equals to 1, this condition is called as reset condition or logic 0 state. Now case 3, when s equals to 1 and r equals to 0. Now s equals to 1 and r equals to 0. Now in this condition, r equals to 0 means output of first NAND gate should be forced to be equals to what? 1. Why? Because the output of NAND gate will be high when any one input to the NAND gate is low. Now here the input to the NAND gate 1 is low, that's why output of first NAND gate will be high, that is q equals to 1. So when r equals to 0, then q forced to be equals to 1. Hence both the inputs to the NAND gate 2, because the output of first NAND gate is one input to the NAND gate 2. So both the inputs to the NAND gate 2 are 1, because s is already equals to 1 and due to q equals to 1, both the inputs to the NAND gate 2 are 1. Hence q bar equals to what? 0. Why? Because total number of two inputs which are equals to 1, that is s equals to 1 and q equals to 1. That's why q bar equals to 0. Thus with s equals to 1 and r equals to 0, the outputs are q equals to 1 and q bar equals to 0. And this state is called as an set condition or logic 1 state. Now let's take last, that is s equals to 1 and r equals to 1. Now if q equals to 1 and q bar equals to 0 initially, then the inputs to the NAND gate 1 are 1 and 0. Therefore its output, that is q, will continue to be equal to 1. Similarly, the inputs to the NAND gate 2 are 1 1. Therefore its output, that is q bar, will continue to be equals to 0. Thus there is no change in the outputs. Similarly, if we check another condition, that is if suppose q equals to 0. Now why we are going to check these conditions? Because s equals to 1 and r equals to 1. For first three conditions, that is 0 0 0 1 and 1 0, it is possible to predict what will be the output of that particular NAND gate. Because as per the truth table of your NAND gate, if any one input is low, then output is compulsory to be high. But for this case, s equals to 1 and r equals to 1. That's why we are going to check these two conditions. That is when q equals to 1 and q equals to 0. Now for second condition, if suppose q equals to 0 and q bar equals to 1 initially, then the inputs to the NAND gate 1 are 1 1. Therefore its output, that is q, will continue to be equals to 0. Similarly, the inputs to the NAND gate 2 are 1 and 0. Therefore its output, that is q bar, will continue to be equals to 1. Thus there is no change in outputs if s equals to r equals to 1. Thank you.